National Electrical Code Section 250.36 addresses the sizing of grounding electrode conductors in separately derived systems. It is crucial to understand when the exception to this rule applies, particularly concerning bonding jumpers. The core rule in 250.36 relates to the connection of a bonding jumper between the grounded conductor terminal of the separately derived system and the grounding electrode conductor. The exception to this rule, specifically exception No. 1, states that the size of the grounding electrode conductor shall not be smaller than that of the supply side bonding jumper, but never smaller than number 10 AWG. This exception only becomes relevant when the bonding jumper is connected to the grounded conductor in accordance with 250.36. To break this down further, consider a transformer acting as a separately derived system. If the bonding jumper is located at the secondary distribution system, or SDS, the critical point is that the bonding jumper is not connected to the grounded conductor terminal of the separately derived system itself. Because of this physical separation, the exception in 250.36 does not apply. This means that the grounded conductors, if run in parallel, can be smaller than 1/0 AWG. It is absolutely critical to note this is only the case if the bonding jumper is located at the secondary distribution system and therefore not connected to the grounded conductor terminal of the separately derived system. Let's clarify the terminology we're using. A separately derived system is an electrical source, other than a service, that has no direct electrical connection to the service conductors. This could be a transformer, a generator, or an inverter. The grounded conductor is the conductor of a circuit that is intentionally grounded, providing a return path for fault current. A bonding jumper is a conductor that connects the non-current carrying metal parts of equipment to the grounded conductor or the grounding electrode conductor, creating a low impedance path for fault current. The grounding electrode conductor connects the system's grounded conductor to a grounding electrode, such as a ground rod or a metallic water pipe. The secondary distribution system, or SDS, refers to the portion of an electrical system that distributes power from a transformer or other source to the final loads. When applying these concepts, the location of the bonding jumper is the key. If the bonding jumper is at the SDS and not connected to the transformer's grounded conductor terminal, the standard rules for grounding electrode conductor size apply, allowing for smaller parallel grounded conductors. However, if the bonding jumper is connected directly to the transformer's grounded conductor terminal, the exception in 250.36 applies, and the grounding electrode conductor must be sized according to the supply side bonding jumper, but not smaller than number 10 AWG. To illustrate this with an example, imagine a 480 volts to 208 volts/120 volts transformer stepping down voltage for a building's lighting and receptacle circuits. If the bonding jumper is located at the transformer, connecting the transformer's neutral point to the grounding electrode conductor, the exception in 250.36 comes into play. In this scenario, the grounding electrode conductor must be sized at least as large as the supply side bonding jumper, with a minimum size of number 10 AWG. However, if the bonding jumper is located at a panel downstream from the transformer, serving as the SDS, and is not connected directly to the transformer's neutral, the exception does not apply. The grounded conductors can then be sized independently, potentially smaller than 1/0 AWG if run in parallel and meeting the requirements for ampacity and overcurrent protection. It's important to consult the specific tables and requirements within the National Electrical Code for accurate conductor sizing based on the system's voltage, current, and grounding configuration. Always consider the ampacity of the conductors, the overcurrent protection provided, and the applicable dirting factors for ambient temperature and conductor bundling. Remember to verify the authority having jurisdiction, or OJ, for any local amendments or interpretations of the National Electrical Code that may affect the installation. For example, in some jurisdictions, specific requirements for grounding electrode systems may exist, mandating the use of specific grounding electrodes or requiring additional bonding connections. Understanding the nuances of 250.36 and its exception is critical for safe and compliant electrical installations in separately derived systems. Paying close attention to the location of the bonding jumper and its connection to the grounded conductor will ensure that the grounding electrode conductor is appropriately sized, providing a reliable path for fault current and minimizing the risk of electrical shock or fire. In summary, if the bonding jumper is located at the separately derived system, specifically connected to the grounded conductor terminal, the exception in 250.36 applies, and the grounding electrode conductor must meet the size requirements based on the supply-side bonding jumper. Conversely, if the bonding jumper is located at the secondary distribution system and is not connected to the grounded conductor terminal of the separately derived system, the exception does not apply, and the grounded conductors can be sized independently, potentially smaller than 1/0 AWG when run in parallel. Careful consideration of these factors is essential for ensuring a safe and code-compliant electrical system. Let's reiterate the key differences. When the bonding jumper is at the SDS and not connected to the transformer's grounded conductor terminal, the exception in 250.36 doesn't apply. This allows for more flexibility in sizing the parallel grounded conductors, potentially permitting sizes smaller than 1/0 AWG, provided they meet other code requirements such as ampacity and overcurrent protection. However, if the bonding jumper is directly connected to the transformer's grounded conductor terminal, the exception is active. This mandates that the grounding electrode conductor size must be at least as large as the supply-side bonding jumper, with a minimum of number 10 AWG. The rationale behind this distinction lies in the path of fault current. When the bonding jumper is at the transformer, it establishes a direct, low-impedance path for fault current to return to the source. The grounding electrode conductor plays a critical role in this path, ensuring that fault current can quickly trip an overcurrent protective device such as a circuit breaker or fuse. By requiring a larger grounding electrode conductor in this scenario, the code aims to enhance the safety and effectiveness of the grounding system. Conversely, when the bonding jumper is at the SDS, the fault current path is less direct. The grounded conductors themselves play a more significant role in carrying fault current back to the source. As long as these conductors are properly sized to handle the available fault current and are protected by appropriate overcurrent devices, a smaller grounding electrode conductor may be acceptable. The National Electrical Code provides specific tables and guidelines for calculating fault current and determining the appropriate conductor sizes. These calculations take into account factors such as the system's voltage, impedance, and available fault current. It's essential to perform these calculations accurately to ensure that the electrical system is properly protected against faults. Let's delve a little deeper into the practical implications of these rules. Consider a large commercial building with multiple transformers serving different areas. Each transformer represents a separately derived system, and the location of the bonding jumper for each system must be carefully considered. If the bonding jumpers are located at the transformers themselves, the grounding electrode conductors must be sized accordingly, potentially requiring larger conductors and more robust grounding electrodes. This can add to the cost and complexity of the installation. However, if the bonding jumpers are located at the SDS panels downstream from the transformers, the grounding electrode conductor requirements may be less stringent, potentially resulting in cost savings. The choice of where to locate the bonding jumpers should be made in consultation with a qualified electrical engineer, taking into account the building's electrical load, the available fault current, and the applicable code requirements. In addition to the location of the bonding jumper, other factors can also influence the size of the grounding electrode conductor. These factors include the type of grounding electrode used, the soil resistivity, and the presence of other grounding electrodes in the vicinity. The National Electrical Code provides guidance on these factors and how they should be considered when designing a grounding system. It's important to remember that grounding is not a one-size-fits-all solution. Each electrical system is unique, and the grounding system must be tailored to the specific characteristics of that system. A thorough understanding of the National Electrical Code and the principles of grounding is essential for ensuring a safe and reliable electrical installation. Furthermore, regularly inspecting and testing the grounding system is crucial for maintaining its effectiveness over time. Grounding electrodes can corrode or become damaged, and bonding connections can loosen. Regular inspections can identify these problems before they lead to safety hazards. Testing the grounding system, such as measuring the ground resistance, can verify that it is functioning properly. If the ground resistance is too high, it may indicate a problem with the grounding electrodes or bonding connections. In such cases, corrective action should be taken to restore the grounding system to its proper condition. Grounding is a critical aspect of electrical safety, and it should never be overlooked. By understanding the rules and principles of grounding and by following the guidelines in the National Electrical Code, you can help ensure a safe and reliable electrical system. To recap, the decision to apply the exception in 250.36 hinges on the location of the bonding jumper. If the bonding jumper connects to the grounded conductor terminal at the separately derived system, the exception applies, mandating a grounding electrode conductor size no smaller than the supply side bonding jumper, but not less than number 10 AWG. Conversely, if the bonding jumper is situated at the secondary distribution system and does not connect to the transformer's grounded conductor terminal, the exception is not applicable. This allows for parallel grounded conductors to be smaller than 1/0 AWG, contingent on meeting other code-mandated requirements for ampacity and overcurrent protection.